So let's talk about the code for merge sort. We're going to take the list, and then we're going to take two more parameters that tell us the bounds, the part, indicate to us the part of the array that we are sorting. This setup should look pretty familiar, where you're writing a recursive function and you get a start and an end, or a low and a high, or something like that. I think all three, or at least two out of the three programs, recursive functions you had to write in the recursion assignment were set up that same way, right? So fairly common. So in merge sort, what is the base case going to be? Any ideas? You can say it either in code or in just conceptually. Go ahead, Patricia. See there's something in the chat.
Oh, my idea was just that the start is the same as the end.
Okay. So if the start is the same as the end, that would mean that we have a list of length 1, right? So that makes sense. That would be sorted. Just to be safe, I'm going to actually say if start is less than or equal to 10. That's going to be my, that would be my recursive case. So the base case would be if start is greater than n. That makes sense? That means they, or greater than or equal to, right?
Yeah, you might as well make the base case when it's one long.
Yeah.
Don't have to do anything else. Don't have to add another function.
Exactly. So I'm going to make this start is less than end. Sorry, that's not the base case, right? That's the recursive case. But as it turns out, in the base case, what do we want to do? I guess I should just spell it out here. So the base case would be the opposite of that, right? If start we're going to equal to, what do we want to do in that case? Well, nothing. We're done, right? So in a case like this, what we do is we just reverse the condition. And so then we have a base case there sort of implicitly. Hopefully that'll make sense. So I'm just going to say if start is less than end, do the recursive case. And that's the whole function. The recursive case, I'm sorry, the base case, it may look like it's not there, but it actually is there because the base case is when this is not true, and then we just do nothing, right? That makes sense. I'll get into the base case there. Okay, so recursive case. What we want to do is we want to sort the left half of the array, sort the right half of the array, and then merge those two lists back together again, right? That was our strategy. So just going back up here and looking at our diagram, that's what we've got here. We've got the whole list, and what we're doing is we're going to split it into half. We're going to sort the left half, sort the right half, okay, and that's what all of this stuff down here is. So now we've sorted the left half, and we've sorted the right half, and then we're going to merge those two lists back together again. That's the strategy. So that actually turns out to be pretty darn simple in terms of the code. It's just going to be merge, sort, the list, starting at start, going up to the middle point, which would be start plus 2. Oops. Does that make sense? Call the function recursively, starting at start, going up to the midpoint. Let me insert some rows here. Any questions about that line? So sort the left half of the list, and then go start at start plus 1 and that's sort the right half of the list, and then just merge them together. So I'm going to call a function that does that, merge, and all my merge function is going to have to know is it's going to have to know the list, and then it just tests in the start and end, and it can figure out where the dividing line is between the two lists that it is merging. So other than the fact that we have to write this function in merge, that's it. We're done with merge sort. Any questions about that? I mean, I don't know about you, but I kind of love the sleekness, I guess, of recursive solutions like this. Any questions? Okay, so let me show you merge real quick. So merge is going to be a function that's going to take, it's basically going to take this, let's look at this example right here. So if we're looking at this area right here, the merge function is taking two lists that are sorted and merging them together into one list that's sorted. And I actually went through that merging process with you in quite a bit of detail, I remember last time. Right? We have a counter or an index pointing into the left array, an index pointing into the right array. We see which one is smaller. Whichever one is smaller goes down into the resulting array, and then we bump that index up and we repeat the process. So that's going to look like if you can see this code over here. That's a little bit scary, right? It actually turns out that this code it's not that hard. It's not very dense code at all, but it's just kind of long and a little tedious. But you can see that I'm going to have 3 counters. I'm going to have a count that is going to be the index in the new list that we're forming. Oh, by the way, just backing up a little bit. We are going to need to have a second array. So we're going to actually create a new array on the heap. And we're going to create our sorted merged list in that new array. And then at the end, we're going to copy it back into the original array. That part make sense? Oh, is that better?
Yes.
All right.
Yes.
Okay. Did you catch that part about the creating a new array? Should I say that again?
Yes.
Okay. All right, so I'm going to have 3 counters. I'm going to have a counter in the newly formed array. I'm going to have a count called left that's pointing in the left half of the array, and I'm going to point that. I'm going to have a counter called right that is pointing at the array, the list that's in the right half of the array. Okay, and so I'm going to say while but yeah, a long story. I know why it happens. So I forget to do something, but so tell me this loop makes sense. Okay, what I'm saying here is I'm going to keep going as long as the left index hasn't reached the end of the left list and the right index hasn't reached the end of the right list. Okay, so I've got looking at these 2 lists here as an example. I'm going to have left pointing at the 55, right pointing at the 38, and then count is going to be down here in the new array that hasn't been filled up yet. Okay, so this array down here is going to be start off being uninitialized. Okay, so I'm just going to say whichever one is smaller, right? So if the one on the left is smaller, put it into the new temp array and increment left. Otherwise, put the value on the right into the new array and increment right. Okay, so in this particular example, right's going to start off pointing at the 38. I hope it's okay I use the word pointing at, even though it's not a pointer, it's an index. So right is going to be pointing at the 38, left is pointing at the 55. The list of left is not less than or equal to the list of right. So we're going to do the else part, which means we're going to put the 38 here and then increment right. So it's going to be pointing at the 67. All right. So keep doing that until one of these 2 reaches all the way to the end. Then what this does is it says, okay, if there's anything left in the left sublist, let's go through and add those to the end. So for example, if we made it all the way through the right sublist and there were still 3 or 4 items left over here in the left sublist, just copy those up for 3 or 4 items down, because we need to just get those in there. And then this is taking care of the opposite situation where we've got items left in the right sublist. We reached the end of the left sublist and there's still items left in the right sublist. Then this is where we just copy from that temporary array that we created back into the original array. And then we delete that temporary array. Okay, so that's the merge function. A little tedious and long, but really not all that complicated. All right, any questions about merge sort? Okay. I really think that everybody can, this is code that is accessible, right? This is not like code that you can't understand. You should be able to look at that and stare at it for a while and really understand what's going on. Okay, back to quick sort. Okay, so here's our list of numbers. What we're going to do with quicksort. Okay, so I started to say, quicksort is similar to merge sort in that there's going to be this process of dividing the list in half over and over again and sorting each half. But instead of sorting each half and then merging them together, what we're going to do is we're just going to take all of the smaller items and put them in the left half of the list, and all of the bigger items and put them in the right half of the list. So neither list is going to be sorted, but everything in the left list is going to be smaller than everything in the right list. Okay. The details for how we do that are somewhat complicated. The first thing we're going to do is we're going to pick a number to be what we call a pivot. Okay, and that number that we pick to be the pivot is going to be, what we're going to do is we're going to look at every number in the array, and if it's less than the pivot, we're going to put it in the left half of the array, and if it's greater than the pivot, we're going to put it in the right half of the array. So when we're done, everything less than the pivot will be to its left, everything greater than the pivot will be to its right. Okay? One of the big challenges in computer science that people write papers about and stuff is how to pick what the best way is to choose that pivot. There's lots of complicated ways to do it. What we're going to do for our purposes is we are just going to say, okay, let's take the last element in the array and we're going to make that the pivot. Okay? So here's what we're going to do. The pivot is 60. We are going to start an index from the left. I'm going to just put L here. And we're going to start an index from the right. Okay. We are going to move L up until we find an item, an element that is bigger than the pivot. We're going to move R down until we find an item that is less than the pivot. So L is already at an item that's greater than the pivot. R is already at an element that's less than the pivot. So in this case, we're not going to move them at all. And then what we're going to do is we're going to swap those two elements. So I guess what I should have done is first make a copy of this. Okay, here's L, here's R. L is pointing at something that's greater than the pivot, R is pointing at something that's less than the pivot, so we're going to swap those two. Okay, now we're going to move L, so we're going to just repeat that process over and over again. Move L up until we get it to a number that is larger than the pivot. So L is going to move to there. Move R down until we get to an element that is less than the pivot. And then swap those two, 35 and 92. Okay, move L up until I find a number greater than the pivot. So that's going to be the 67. Move R down until I find a number less than the pivot. So that's going to be the 53. Swap those two. Move L up until I get to a number greater than the pivot. Move R down until I get to a number less than the pivot. Swap those two. Okay, now I'm going to tell you that the loop is a little more complicated. When I move L up, I'm moving it up as long as the number is less than the pivot, and also I haven't reached R, right? So as soon as L reaches R, it just stops. So I'm looking for a number greater than the pivot. 38 is not greater than the pivot. 90 is greater than the pivot, but that doesn't actually matter because I've hit R, and so that means I'm just going to stop. L and R are both pointing here at the 90. Okay. At this point, what we do is we swap this item, where left ended up, with the pivot. So that's how we end up at the end. We get the pivot into the middle of the list. As we swap wherever we end up, we swap that number with the pivot. So 60 goes here, 90 goes here, and I'm just going to put a boxer on the 60 to indicate that that was the pivot. So watch, it took me like 10 minutes to try to do that. But, so just leave it there. Okay, any questions about that first step and what we end up with? What we end up with is we've got a pivot in the middle. Everything to the left of the pivot is less than the pivot. Everything to the right of the pivot is greater than the pivot. So all that swapping around and moving L up and moving R down, the whole point of all of that was to get the situation where everything on the left of the pivot is less than the pivot. Everything on the right of the pivot is greater than the pivot. Okay. So now what we do is we do that same process again with each half. Right? So this is gonna be a recursive call when we see the code. We're gonna call quicksort on the left half. We're gonna call quicksort on the right half. Okay? Let's do it a couple more times. So the 38 is gonna be the pivot. Just focusing on the left sublist here. 38 is the pivot. So L goes there, R goes there. Move L up until I get to a number greater than the pivot, already there. Move R down until I get to a number less than the pivot, already there. Swap the 43 and the 15. Move L up until I get to a number greater than the pivot. Move R down until I get to a number less than the pivot. That would be the 35. Swap those two. Move L up until I get to a number greater than the pivot, or I meet R. So now L and R are both pointing at the same place. And then now I'm going to swap the 55, which is where we ended up, with the pivot to get the pivot in the middle. So 38 and 55. And I'm going to put a box around the 38 so we know that was the pivot. Okay. All right. So I'm going to do this again over here on this side. There's a couple of very minor details that I have left out of this just for the sake of keeping things simple. Actually, just one thing. So I'll cover that this time around. Pivot is 90. L is going to go here. R is going to go here. The funny thing about quicksort is that as the list gets shorter in size, it becomes sort of more difficult to watch it in action. But I think we can go one more round here. Okay, so move L up until we get to a number greater than the pivot. So that will put L here by the 96. Move R down until we get to a number less than the pivot, already there. So swap the 96 and the 82. Move L up until we get to a number greater than the pivot. So L is going to end up there. Move R down until we get to a number less than the pivot, or we meet L, and of course we meet L first. So L and R meet right there. And now, since L and R have met, the last step is to swap where they met with the pivot. The only thing I'm going to say here is that because of some very special rare cases, we have to say if this number in the middle is greater than the pivot, do the swap. Okay? And in this case it is, 92 is greater than 90, so we're going to do the swap. And I'm going to put a box around the 90 because that was the pivot. Okay. All right. We're going to keep going on this, but I want to pause there and just talk about a couple of things. One is I actually, at some point, maybe 3 or 4 or 5 years ago, spent literally an entire day working on my quicksort code because I kept breaking the code that I found either in a textbook or online. Like the code would work, like I was just running it with it, all sorts of different data samples, and I would run it and it would work and it would work, and then something would fail. So this is super, super hard to get exactly right. My experience is that a lot of the examples of quicksort that you find in a textbook or online actually don't work all the time. So anyway, the other thing I was going to say is in actual real life with quicksort, at a certain point, you're going to stop calling quicksort recursively and you're just going to sort the numbers. And, you know, there's research done on what size that is. And honestly, I can't remember off the top of my head. It actually turns out to be remarkably consistent, but I don't remember what the number is. I think it's like maybe around 10 items in the list or something like that. Just stop calling quicksort and use insertion sort to finish it up. But we're not going to do that. We're going to use quicksort all the way up until we are totally done. So let's go again. Right here we have a list with 2 items in it. I'm going to just plow my way through this algorithm, doing exactly what the algorithm says to do. So it says pick a pivot. 35 is going to be the pivot. We're going to set L to the left element in the list, and then we're going to set R to the element to the left of the pivot, which in this case turns out to be the same. Okay, so now our loops where we move L to the right and we move R down to the left aren't going to happen because L and R have already met. So at this point, we're at the point where we would normally swap where they met with the pivot. But this is that special case I was telling you about where in this particular case, we don't want to do that swap because the place where L and R met turns out to not be bigger than the pivot. So we're not going to even make a swap. All we're going to do is, whoops, first I should make a copy of this. I should have made it, there should be another line here, rats. Anyway, so I'm just going to put a box around the 35 because the 35 was the pivot when I sorted the list 1535. Oh, that's not what I have. Oh, well. You'll have to pretend there's another, you'll have to pretend there's another row in here, right? I forgot to make a copy of it. So there's actually should be one additional pass that isn't showing up here. All right, then over here, we've got a list 53, 43, 55. So we choose 55 as the pivot. L goes here. R goes here. We move L up until we get to a number greater than 55. But we don't find one. We meet R first. So now L and R are both pointing there. We check to see if we're supposed to swap with the pivot. We are not supposed to swap with the pivot because it's not greater than the pivot. So now I've got 55 was the pivot, and I still have a list here with 2 items in it that we haven't sorted yet. Over here, I've got a list with 2 items in it. What we found out, well, let me just go through it. So it takes 82 to be the pivot. L is going to go here. R is also going to go here. Since they've already met, we check to see if we should swap them. Because the 67 is not bigger than the pivot, we don't swap them. we just leave it the way it is, and we say 82 is the pivot. So that leaves us with a list of size 1 here with the 67, and a list of size 1 here where the pivot was. And then 96 and 92. So this is different from anything we've done so far, right? Because it's the first time we have a list of length 2 with the numbers in the wrong order. So 92 is going to be the pivot. L and R are both going to go right here. They have already met, so we don't move them. And we just check and see if this is bigger than the pivot. It is bigger than the pivot, so we swap them. And 92 is the pivot, so I'm going to put a box around it. Okay? And you can imagine that we would do this one more time, right, to get the 53 and the 43 in the right order. I'll just get this done real quick. So 43 would be the pivot. L and R would both be pointing at the 53 because the 53 is bigger than the 43 because the point where L and R met is larger than the pivot. We're going to swap that element with the pivot. So it becomes 43 and 53, and we box the 43 to show that it was the pivot. Okay? How's that look? Any questions? I know that's a little complicated, but I think that you can do it. Yeah, go ahead, Patricia.
The code may answer these questions that I have, but I was wondering if this gets split into like smaller lists or arrays. And
So, go ahead, sorry.
And I was just wondering if it gets split all the way until it's like of size 1 or of size 2.
So the way that, I mean, I think what I just demonstrated is, yes, we're splitting it up into, not into literally physically different arrays. The way we split it up is the same way we did with the merge sort. We just changed the values of start and end, right?
Oh, okay.
And that's the same thing we did with merge sort, right? We said, okay, call merge sort with start equal to 0, and let's say the size of the array was 12. Okay, now start's going to be 0, end is going to be 6 or 5, I guess. 0 plus 11, yeah. And then call merge sort again, sending it the same list, but starting at 6 and going up through 11. So we'll do the same thing with quicksort. Yes, that's true. Merge sort required the temporary array, but that really didn't have anything to do with splitting it up into smaller arrays. That only had to do with when we had to take those smaller arrays and merge them back together again. And right, well, that's actually something that slows merge sort down quite a bit, is the fact that it has to create a new array, copy everything into the new array, copy the new array back into the original array. Quicksort doesn't have to do any of that. But the answer to your question, Patricia, is yeah, we're splitting this up. And as I mentioned a minute ago, what I showed you just now and what we'll be doing in the code is we're actually going to just keep splitting the lists up until we get down to lists of size 1. In real life, if you were doing this in real life and you were trying to write the most efficient quicksort that you possibly could, once you get down to size about 10, and I'm off the top of my head, I can't remember the exact number, but somewhere around 10 or so, you're going to just stop calling merge sort, and you're just going to do some sort of a simple quadratic sort, just because the overhead of all the recursive calls becomes too much of a drag. That answer your question?
Okay, so essentially it's just swapping elements inside the same array.
Yes, exactly.
Okay, thank you.
Well put. Okay. This is going to be a little more difficult because I messed up my diagram here. There should be one more row. But really, we're doing the same thing we did with merge sort. So what I want to ask you now is, how many of these passes are there going to be? And for now, when you answer that question, I want you to just assume that we get lucky in choosing our pivot, and we always choose a number very close to the median of the number, so that the array is going to get split exactly in half. So how many times am I going to have to split the array in half? The answer to that question should be just like automatic by now. We've done this, well, I guess we've only done it twice, but we did it with binary search, and we did the same thing with merge sort, right? If the size of the array is 8, how many times am I going to have to split it in half? 3. If the size of the array is 16, how many times am I going to have to split it in half? 4. So what function is that? It tells us how many times I'm splitting it in half. I'll give you a hint. So this is when we did this using merge sort, right? And I said, okay, if n is 8, the number passes as 3. If n is 16, the number passes as 4. If n is 32, the number passes as 5. That turns out to be it log base 2 event. Okay? That little factoid right there, super, super, super important. You know, if that's not clear, we need to work on that. Hopefully it's clear that if I start with the right column and go to the left column, I can get there by taking 2 to the y, right? 2 to the 7 is 128, 2 to the 6 is 64, 2 to the 5 is 32, and so on. Log base 2 is simply the opposite, or the inverse of 2 to the, okay? So bottom line here for quicksort is, assuming that we pick reasonably good pivots, the number of times we have to divide the array up is going to be log n. Log base 2 of n, but we don't care about the base 2. Okay? Each time we divide the array up, we have to look at every element in the array, right? I mean, we had L and we had R, and we were moving L up and we were moving R down, and we were doing some swapping. So number of I guess I should just abbreviate. Number of operations required for each time we divide the array up is n. So the total number of operations required is going to be n times log n. There's our big O of quicksort. Anyone want to ask a question about that? All right. Anything else you want to talk about before we take a look at the code for quicksort? All right, so what's wrong with my keyboard? Okay. We're going to have exactly the same. Don't ask me why I used left and right here, and I used start and end on merge sort. Just arbitrary. We're going to have the same base case. So we're going to do the if left is less than right thing. So the base case is when that is not true. Okay. Now we're going to be a little bit opposite of merge sort, because on merge sort, we recursively sorted the left half, and then we recursively sorted the right half, and then we merged them. With quick sort, we do the opposite. First, we divide it into two halves with the smaller items in the left half and the bigger items in the right half. And then we call quick sort on each of those halves. So I'm going to just create a function named partition, which is going to take the two lists and do the whole, I can't talk and type at the same time. Okay, so what this is doing is it's doing that process we did of shifting all of the smaller items to the left and all of the bigger items to the right. And then it's going to return the position, the index that the pivot ends up in. So then all that's left is we're going to quick sort the left half. So that's going to start with left and go up to pivot -1. And then we're going to quick sort the right half. So start with pivot +1 and go up to right. So that's our code for quicksort. All that's left is we have to write this partition function. Okay. Any questions about that code? All right. Want to see the real deal? The partition function?
Yes.
I thought you might. All right, I guess I will keep the Excel spreadsheet up there too in case we want to refer to it. So I will share my screen. Okay, so here's the quicksort function. Here's the partition function. I'm hoping we can go through this code and you can say, that line corresponds to when Dave was doing this, when he was, tracing through the example. Pivot gets lists of right. That makes sense, right? Every time we had a list, I said, okay, the pivot is the item clear at the right. Then index from right, that's the capital R that I was using. That starts off 1 to the left of the pivot, so that's right -1. The big L I was using, index from left, starts off at the left end of whatever the portion of the array is that we are sorting. Okay, now I'm just going to have this big while loop that says while index from left is less than index from right, move left up as long as the item that it's looking at is less than or equal to the pivot. So in other words, move left up until you find something greater than the pivot, or you meet index from right. Okay, we did that. Now here's where I moved R down until I found a number less than the pivot, or I met the index from the left. Then this is where I say, if they didn't meet, right, if they met, I don't have to do this, but if they didn't meet, go ahead and swap those two. And then start over again, right? As long as index from left is less than index from right, move L up, move R down, swap. As long as they haven't met, move L up, move R down, swap. And then, okay, let's say they meet. So that means we're done with the partition. And so here's where we say, the important line here is this, right? Swap list sub that L So wherever L and R met, so that could just as easily be indexed from right because they've met at this point. Swap list sub index from left with the pivot, which is that list sub right. And then we're going to return the index of wherever the pivot ended up. Okay. And then this if statement is just that little final detail that I gave you towards the end where I said, just to be super careful, we want to make sure we only do this swap if the point where L and R met is bigger than the pivot. Otherwise, we don't want to do that swap. Okay. All right. I hope that it's hard for me to get a sense of like if this code just makes total sense or if it's just mysterious. But if it is mysterious, I hope that you can take the time and look at it, stare at it for a while because it's pretty cool stuff. And once you get it, it's not all that hard. Important thing that I'm going to have you guys actually do in the homework is this stuff over here, right? For all of these, 7 algorithms that we've talked about now, right? If I go way back up to the top, here's the 7 algorithms that we talked about. I'm going to ask you to actually diagram them out to show me that you understand how they work. Okay? So you'll have that in the homework. If you get stuck in the homework, just make sure you let me know. It'd be great if you could get a start on that. And then if there were questions, we could talk about them on Thursday, but I can understand if that's not possible. Anything else you guys want to talk about? My plan is to stop there, and then on Thursday we will start on the next topic, which is queues. Queues and priority queues. All right. I guess I will see you on Thursday.
Sounds good. Thanks.